All right, today we're going to look at elevators. We're also going to look at rockets. It's not included in the title here. And inclined planes. So our goal is obviously to draw free body diagrams, but also calculate force vectors when movement is in a vertical or inclined plane. So we're going to see that obviously the elevators move in a vertical direction, rockets also, in an inclined plane. Well, that's self-explanatory. Okay, so suppose we attach a rope to a steel ball and then hold that ball up by the rope. There are two forces acting on the ball. So if we have our ball, we've obviously got gravity, as always. And if this was attached to a rope, along that rope, we also have the force of tension. Okay? So, this takes the place of the normal force now because the object is hanging from that rope. If the object is not moving up or down, we know that these forces are balanced. We also know they're balanced if it is moving up or down at a constant speed. Excuse me. And if Ft is larger than Fg, the ball is going to move up. If Fg is larger than Ft, the ball will move down. Okay, so a rope is attached to a 50 kilogram mass. What is the tension force required to accelerate this mass upwards at 2 meters per second squared? So let's draw our force diagram. We always have the force of gravity. And because it's attached to a rope, it has a tension force. We know that the mass is 50 kilograms, and the overall acceleration of this mass is 2 meters per second squared. So, what I'm going to do is calculate the net force. Remember, that's mass times the acceleration of the object. So we have 50 kilograms times our positive 2 meters per second squared because it's going up. And we get 100 newtons, which is positive. Oops. So, we can also at this point calculate Fg because we have the mass and we obviously know gravity. And I got negative 0.5 newtons. All right. Overall, F net is equal to Ft plus Fg. Again, we'll put signs in to account for their direction. F net was positive 100. We are going to find Ft, and Fg was negative 490.5 newtons. Moving that all around, we get that Ft is equal to positive 590.5 newtons. So technically, I should be writing this as 5.9 times 10 to the 2 newtons, and because it's positive and we were talking about up down, this is upwards. Remember, force should have a direction. All right. A rope is attached to the same 50 kilogram mass. What is the tension force required to lift the mass upward at a constant speed? If it is constant, that means that Ft equals Fg. And if it's constant, again, the overall force is 0. And again, this is because F net equals mass times acceleration. Acceleration in this case is 0, therefore F net is 0. All right, force diagram, surprise, Fg and Ft. So the magnitude of Ft must equal the magnitude of FG. All right, and again, they're in absolute values because I know that their direction is opposite, so their signs I'm not really considering here. So FT is equal to the absolute value of M times G then, which is 50 kilograms times negative 9.81 meters per second squared. And the absolute value is 490.5 newtons. So therefore, Ft is equal to 4.9 times 10 to the 2 newtons up. All right, a rope is attached to a 50 kilogram mass. If an upward force of 280 newtons is applied on the rope, what is the resulting motion, aka acceleration, of this mass? Ft and Fg again. Ft we know is 280 newtons. So let's calculate Fg. times negative 9.81 meters per second squared, and we get negative 490.5 newtons. So F net is equal to Ft plus the force of, gravity. And we will get Ft was positive 280 newtons. Fg is negative 490.5 newtons. F net is negative 210.5 newtons. So we can use F net equals mass times acceleration. We get that 210.5 newtons, that's negative overall, is equal to 50 kilograms times the acceleration. And we get that acceleration equals negative 4.21 meters per second squared. Because we're moving in a vertical direction here, negative means down. So acceleration is 4.2 meters per second squared down. Okay, elevators. When an elevator accelerates upward, we feel slightly heavier than normal. As the elevator continues up at a constant speed, you just feel normal. But as the elevator slows to a stop, you again feel slightly lighter than normal. So what we feel is the apparent weight. It's not the pull of gravity down on you, but rather the weight of the floor pushing up on you. So in other words, the apparent weight you feel is actually the normal force of the elevator acting on you. So the normal force changes due to the motion of the elevator's floor. So when we are looking for apparent weight, we are looking for Fn. Okay, and we're going to get this using Fg. All right, so F net is always Fg plus Fn. All right, we could organize with negative because we know that Fg is in the negative direction. And so the acceleration of our elevator will actually be put into F net. Okay, because F net, again, is mass times acceleration. So this will be the acceleration of the elevator. And m is always the mass that's being moved in the elevator. Okay, it's not the elevator's mass. Okay, so if we are accelerating up, we know that acceleration, A, is positive. Therefore, F net will be greater than 0. If F net is greater than 0, then Fn has to be bigger than Fg to oppose its negative. Okay, if we are accelerating down, acceleration is negative. Therefore, F net will be less than 0, aka negative. If F net is negative, then Fn is small. Or smaller than Fg. And if the elevator is moving constant or not at all, F net equals Fg. Okay, let's put this into play because I think it's easier when you see it in an example. It seems complex, but I promise you guys are going to be good at this. Okay, in an elevator, if you normally weigh 706 newtons, this is Fg when your weight. What is your apparent weight, aka what is Fn? If you're in an elevator that is slowing down at a rate of 1.65 meters per second squared. So in an elevator, we have Fn and we have Fg. All right. We know in every case here, F net equals Fn plus Fg. All right. So let's calculate F net because we have the acceleration of the elevator. So it's mass times acceleration, which is, we don't have mass. So we need to calculate that using Fg. Okay, so we have Fg, it's 706 newtons. And that will equal some mass, remember it's downwards, sorry, times acceleration. So we get that our mass is 72 kilograms. Okay, so we can always find mass from Fg, given that we're on Earth. Okay, so putting that mass in, we get 72 kilograms times our acceleration is slowing down. Therefore, it's a negative. Oh, I'm out of room there. Okay, if that is negative, we get 72 times negative 1.65. I solved it all in one go on my actual piece of paper here. So that's negative 118.8 newtons. All right, putting this in our formula all together here, we get that F net was negative 118.8, and we are looking for the normal force, or the apparent weight, and Fg is negative 706. So moving things around here, we get that Fn equals positive 587.2 newtons. Therefore, 3 sig figs, we get 587 newtons upwards is the apparent weight. Okay, rockets. Thrust of a rocket is what we're talking about here. So the thrust of a rocket comes from two things. It overcomes the force due to gravity that's acting on the rocket, okay, and it accelerates the rocket upward. In my drawing here, it's missing the information, but our rocket force of thrust is moving upwards, and Fg is holding her back. The action force is the rocket engine actually pushing gases down and out of the rocket. Okay, so how we get moving is actually these forces pushing down, and the reaction force in opposition is actually those gases pushing back up on the rocket as they bounce off the ground. Okay, simpler than it looks again. Our 1,200 kilogram rocket produces 30,000 newtons of thrust. What is the velocity of the rocket 45 seconds after launch? So if I want to find a velocity, I know that the rocket is accelerating. Sorry, so we need to find acceleration first. We can do that, finding F net. That will give us mass times acceleration, so we can find A. So draw this. We get F, force of thrust. Carefully, you don't just write F of T, because F of T is force of attention. So you do actually have to kind of write it out. Okay, we have two forces. F net is equal to the sum of those. Fg, I'm just going to calculate in here if you don't mind. So thrust is upwards. It is 30,000 newtons. Plus the force of gravity is 1,200 kilograms times the gravity. So negative 9.81 meters per second squared. And this negative here is actually going to change this sign so I know that they are in opposition of one another, Fg and F thrust. All right, if you don't like what I'm doing, go ahead and calculate F of G on its own and then just put it into your equation. We're going to get the same answer. Okay, so we get positive 18,228 newtons is my overall F net. So I'll take that and I'm going to break it back down into mass times acceleration. So 228 is equal to 1,200 kilograms times acceleration. Acceleration equals positive 15.19 meters per second squared. That makes sense. We're going upwards, so acceleration should be positive. Now that I have acceleration, I'm going to find a velocity after 45 seconds. So that's a final velocity. What we know is that this rocket started at 0 meters per second. So I'm just going to use our basic acceleration formula. Acceleration equals Vf minus Vi over t. Note that this said A is equal to delta V over delta T in our formula sheet. Delta means the change, so you have to write Vf minus Vi. A few of us have tried to skimp on this and we just put one velocity. This is change. We have to show this. Okay, rearrange and we get that Vf equals A times T plus Vi. Again, these all are vector quantities. So Vf equals acceleration 15.19 meters per second squared times our time of 45 seconds equals 683.55 meters per second. This is a velocity. We do need to say which direction it's going, which I didn't in this question. And significant digits, we should have 2, so 6.8 times 10 to the 2 meters per second. Because it's positive, we are going up. So that's how fast it'll be traveling after 45 seconds. All right, inclined planes. So when I have an inclined plane, our object is here. We draw from the center of its mass. All right, so we draw that Fg is coming straight down from there. We also know that Fn is the normal force and it is 90 degrees to the plane of the object. So the plane of the object is our incline, therefore Fn is moving 90 degrees to that. All right. Our incline has an angle of theta here. And what you need to know is that if I drew this big triangle, the angle theta here, and then this angle, obviously in our 90 must add to 180. So theta and this top angle here must add to 90 together. And what we can see here is that this line here is parallel with gravity, which is still connected to the plane, the inclined plane. So if I were to say that this angle is, I don't know, I think they call it, I'm not even sure what that is, as a variable. Anywho, they call it this variable in our notes here. That's actually equal to this one here. All right, they are the same triangle. They're similar triangles. So if that's the case, the angle between our plane and f of y, which is parallel to Fn, is 90 degrees. All right. So if this is 90 degrees, this variable plus this is alpha, this angle created by solving components of gravity, they must add to 90 as well. So if this and theta add to 90 and this and alpha add to 90, this must mean that theta and alpha are actually equal. All right, so that means the incline of our plane can always be written as the angle to which we break up our gravity components. All right. Going on with all the information on this page, FG, we break into its components, and that FG in the y direction opposes FN, and F of X or FG in the X direction will actually oppose, if this object does not have a force acting on it, it'll oppose friction. Okay. If friction and F of X or FG of X are equal, this object doesn't move. If they are imbalanced, we're going to see the object moving in some sort of direction. Okay, example 6. This 30-kilogram object is on an inclined plane at 40 degrees to the horizontal. What is the acceleration experienced by the object if the coefficient of friction is 0.25? Okay, so let's draw a diagram first and foremost. Okay, so we have our inclined plane and our object sitting on it. Our object we draw from the center, F of N, comes 90 degrees to our incline. All right, F of G comes straight downwards. All right. We have a force of friction holding us back. We are not pushing on this object. It doesn't say that there's any sort of applied force. So friction is holding it up the incline because I know its natural tendency is going to want to come down the incline. So force of friction has to oppose that. All right. Our angle here, I'm running out of room, is 40 degrees. All right. So what we're going to do is we need to break the force of gravity into an X and a Y component. So I'm going to call this FG of Y and FG of X. All right. Now, remember from that first slide, or that last slide, sorry, this will also have an angle of 40 degrees. Okay, and these are 90 degrees to one another. So we're going to solve for the components of FG. So FG in the Y direction. Oh, we need to put in our numbers. So sorry. We don't know what FG is yet. So we need to calculate that off to the side. So FG is equal to M times G. Our mass was 30 kilograms, and we're going to multiply that by negative 9.81 meters per second squared. So the force of gravity is negative 294.3 newtons, or 294.3 newtons down. Okay, now we can actually solve for components. Sorry, jumped the gun there. So, using our trig components here, we get that our 294.3 newtons times the cos of 40 degrees is equal to 225.4 newtons. And FG in the X direction is 294.3 newtons times the sine of 40. And that equals 189.2 newtons. Okay, we've solved our components. What I'm also going to do is just set my positives and negatives. Now this kind of makes, I'm going to copy basically our north, east, south, and west here. But because our actual diagram now is set at a bit of an angle, we just need to define what we're using as positives and negatives. So negative, positive, negative, and positive in this direction. All right. What we can see is in like our north-south, if you will, that the only two vectors that we have is the normal force opposing gravity in the y. Because the object is not being lifted up, we know that these are equal and opposite. So we can say that, oops, I need my pen again. The normal force is equal to gravity in the y. All right, and absolute value again, because obviously their directions are opposite, but their magnitudes are going to be identical. So Fn equals 225.4 newtons. Okay, we have friction in this. So going back to our lesson on friction, I think that was lesson 3. We know that F, the force of friction, is equal to mu times the normal force. Okay, so the force of friction is 0.25 times 225.4 newtons. We get that the force of friction is 56.4 newtons. Okay, so our object, we're going to look at the net force in our x direction, if you will, the x on a tilt direction. So the net force will be the force of friction and the force of gravity in the x direction. Because we know that it is accelerating, we know that these are imbalanced and that there is a net force. So we can say that F net is equal to the force of friction plus the force of gravity in the x direction. The force of friction was, in our case here, because it's moving kind of up, if you will, I decided that that was my positive direction. So it's going to be 56.4 newtons in a positive direction, and the force of gravity in the x direction is moving in a negative, or this direction. So I'm going to say that that is negative 189.2 newtons. So the net force that this is experiencing is negative 132.8 newtons. Okay, the negative is just arbitrary based on the system that I have set here. But I just thought if it's moving down the incline, it should be negative. All right. So last piece here, we just need to go back and say F net is equal to the mass times the acceleration of the object. So negative 132.8 newtons is equal to 30 kilograms times this acceleration. Acceleration is negative 4.43 meters per second squared. So that means it is 4 meters per second squared down the incline. I don't want to just say down because that implies that it was straight down. I'm going to say down the incline to obviously attribute for the fact that it's on that. All right, your homework is all of the odd questions on pages 14 to 17 of the workbook.